Hi everyone. We're really pleased of having Manuel Krannich giving his first lecture about Pontryagin Weiss classes.
Okay, well, thank you for the introduction, and thank you very much for the organizers for inviting me. I did my PhD in Copenhagen, and it's always such a treat to come back here. So, yeah. Okay, all right, maybe let's get something out of the way first. I'll be giving 3 lectures, one every day, starting from today. These conventions hold for all lectures. All the homology groups and all the cohomology groups are with Q coefficients. All manifolds, fiber bundles, etc. are always implicitly assumed to be oriented, and I'm not going to worry about these orientations. Today, I'll give you a little bit of an introduction, state the main result, and then the other 2 lectures start proving the main result, and the other 2 lectures will be about finishing the proof of the main result. And the story I want to tell you is a story about very classical invariants called Pontryagin classes. So perhaps let's start by reminding ourselves what these are. Pontryagin classes are certain characteristic classes of vector bundles. So if we fix a dimension D, then there is an ith Pontryagin class, which is a characteristic class of d-dimensional vector bundles in degree 4i. To remind you, BOD is a classifying space for vector bundles, real vector bundles of dimension D. If we have a cohomology class in there, we get characteristic classes for vector bundles, and these Pontryagin classes are particularly fundamental of such classes. There is one for every natural numbers, and the main properties that they have, which are in some sense more important than their definition, include the following. First of all, they are so-called stable characteristic classes. So what this means is that if you have a d-dimensional vector bundle, pi, and you evaluate the ith Pontryagin class considered as a characteristic class of d-dimensional vector bundles on it, then this does not see the dimension of the vector bundle in the sense that if you add a trivial line bundle, so then this becomes a d plus 1 dimensional vector bundle, you can evaluate the class pi in the cohomology of BOD plus 1, and these 2 values are the same. There are several ways of rephrasing this. For instance, in terms of classifying spaces, this just means that if you pull back pi considered as a characteristic class of d plus 1 dimensional vector bundles along the map iota from BOD to BOD plus 1, that classifies adding a trivial line bundle, then these Pontryagin classes are preserved under pullback along this map. Yet another way of saying this is that the collection of all the PIs for the different values of D assemble to a unique homology class in the classifying space for stable vector bundles. Which is typically denoted BO. So BO is the classifying space for stable vector bundles. So this is just the co-limit over these stabilization maps. Right, okay, so this is the first property. The second property is called vanishing. What this says is that if you evaluate Pontryagin classes of very high degree relative to the dimension of the vector bundle, then they will vanish. More precisely, if you have a d-dimensional vector bundle, then pi will vanish if the degree of the Pontryagin class I is greater than half of the dimension of the vector bundle. And in terms of classifying spaces, we can reformulate this by saying that this stable Pontryagin class in the cohomology of BO, if we pull that back to the cohomology of BOD, then this will vanish for I greater than d half. Okay, so these are sort of, I don't know, kind of properties that you would learn about if you read about characteristic classes in the first course, like for instance following Milner-Stashev or any other textbook. And in these textbooks, and also in the way I presented them so far, Pontryagin classes are presented as invariants of vector bundles. But it turns out that sometime in the 60s, 70s, people realized that actually they depend on a weaker structure, at least rationally, and everything I'm going to say is rational. And this weaker structure I'm going to introduce now. This is a so-called Euclidean bundle. So what's a Euclidean bundle, or also called an RD bundle? This is just a fiber bundle whose fiber is homeomorphic to RD. But there is no linear structure involved. It's an abstract fiber bundle whose fibers happen to be homeomorphic to RD. Whenever you have a vector bundle, you get in particular an RD bundle by forgetting the linear structure on each fiber. And on the level of classifying this spaces, this manifests itself in a map from the classifying space for d-dimensional vector bundles to the classifying space for RD bundles, which is denoted B top D, and is a space that already featured in Sanders' lectures. Incidentally, I'm not sure I mentioned it, I'm going to do it now. Everything I'm going to say is based on joint work with him. Okay, so there's this map, and why would you care about RD bundles? This is something that implicitly also featured in Sanders' lectures. If you have a topological manifold that need not have a smooth structure, let's say of dimension D, then this has an analog of the tangent bundle, which is called the topological tangent bundle. But this is no longer a vector bundle, it is only an RD bundle in this sense. And if your manifold comes with a smooth structure, you take the usual tangent bundle that you're familiar with, and you forget the fiber-wise linear structure, then the resulting RD bundle agrees with this topological tangent bundle. But this topological tangent bundle exists even if the manifold doesn't admit a smooth structure. And there's subjective smoothing theory says that in fact the tangent bundle knows all about the smooth structure. So a topological manifold of dimension not equal to 4 admits a smooth structure if and only if its topological tangent bundle can be refined to come from a vector bundle. And so studying the difference between topological manifolds and smooth manifolds in dimensions not equals to 4 is equivalent to studying the difference between RD bundles and vector bundles, which homotopy theoretically amounts to studying the difference between the classifying space for the former and the classifying space for the latter. And one way of studying this difference is studying the behavior of characteristic classes of RD bundles and of vector bundles. This is one reason why we care about Pontryagin classes, especially those that I'm going to introduce in a moment. So what is the relation to Pontryagin classes and these RD bundles? For that, let's consider the following diagram. We can take the classifying space for d-dimensional vectors bundles. We can use this stabilization map that classifies adding a trivial line bundle. We can go all the way to the classifying space for stable vector bundles. And we can write down the same row for RD bundles. There's this classifying space for RD bundles. We can also add a trivial line bundle to an RD bundle, which is just given by crossing with R. If you have a fiber bundle with fiber RD, you can cross its total space with R, then you get a new fiber bundle whose fibers are homeomorphic to RD plus 1. And taking the co-limit over these stabilization maps, we get a classifying space for stable RD bundles, which is called B top. Any stable vector bundle gives rise to a stable RD bundle, so on and so forth. So we have a commutative diagram like this. Now, the point that was realized, that I was referring to earlier already, that people realized in the 60s, and I'm never sure who exactly to cite for this, but certainly names that were involved are Novikov, Sullivan, Kever-Milner, and then later, I guess if in the version I'm going to state it, I should also put here Kirby-Siebenmann. This is quite classical 60s and 70s geometric topology. They implies that this map from the classifying space of stable vector bundles to the classifying space of stable Euclidean bundles is a rational equivalence. One way of proving this, just as an aside, is using this smoothing theory that I was referring to identify the homotopy groups of the homotopy fiber of this map with the group of exotic spheres, and then using Kever-Milner's work that shows that these groups of exotic spheres are finite. So this map, the homotopy fiber has finite homotopy groups, in particular rationally trivial homotopy groups, and this map is a rational equivalence. Okay. So what does that mean for our Pontryagin classes? Let's apply cohomology to this diagram. The arrows reverse. And the fact that this map here is a rational equivalence in particular implies that this is an isomorphism on cohomology because all my cohomology is with rational coefficients. What this means is that there is a unique, stable characteristic class of RD bundles that agrees with the Pontryagin classes if the RD bundles come from a vector bundle. So this is an isomorphism. There are these Pontryagin classes in here. I take their pre-images and I define them to be generalizations of Pontryagin classes that I can now evaluate at RD bundles and not just of vector bundles. And if these RD bundles happen to come from a vector bundle, then they agree with the usual Pontryagin classes. This is a cohomology class in the classifying space for stable RD bundles. Of course, I can then pull them back to get characteristic classes of RD+1 bundles or of RD bundles. And I can wonder whether those characteristic classes for RD bundles share the same properties that I'm used to from Pontryagin classes for smooth vector bundles. So what about this first property? This first property said that they were stable characteristic classes. But this is the case by the way I constructed them for topological RD bundles as well. I construct them as characteristic classes of stable RD bundles. And then I pulled them back to characteristic classes of RD bundles for a fixed value of D. So this first property is fine. What about the second property, the vanishing? This is less obvious, and people have wondered about that for some time. In writing, the first place where I see that somebody officially wondered about this is in Sullivan's MIT notes, I think from 1970, where he speculated that indeed this vanishing behavior should also hold for these topological versions of the Pontryagin classes. So Pi ought to be trivial in the first 4th cohomology of B top D as soon as the degree of the Pontryagin class is bigger than half of the dimension of the fiber. Okay. Are there any questions so far? In general, please interrupt me. I tend to go rather quick sometimes, but I'm very happy to be slowed down. Okay, well, Sullivan wondered this. Many other people wondered this as well. One of them being Michael Weiss. He wondered about this for a very long time. And at some point, he thought he proved the conjecture, then he changed his mind. Long story. In the end, he disproved this, which came as a big surprise at the time. So there's a theorem that I like a lot. I think it's one of my favorite theorems in recent times by Michael Weiss. So what did he prove? First part is that he showed that this conjecture is not true. He showed that there are
let's state it a bit vague. There are many pairs of degree of the Pontryagin class and the dimension of the fiber such that the degree is bigger than the half of the dimension of the fibers, for which there exists an RD bundle such that the Pontryagin class is non-trivial. And note that this in particular says that this RD bundle cannot come from a vector bundle. Because if it would, then these Pontryagin classes would agree with the classical Pontryagin classes for vector bundles, for which I told you that this vanishing holds. Then the second part is that he showed something much stronger. He showed that they're not just any RD bundles. I can choose X to be very simple, namely to be a sphere. So there are RD bundles over spheres that don't come from vector bundles. And this came, as I said, this came as a surprise. It took some years until the community has digested this. Then some people looked for different proofs. And some years later, Søren Galatius and Oscar Randall Williams came around and gave a completely different argument of a much more classical nature that improves upon one of these two parts of Michael's result. Namely, what they showed in 2022 is that the first part, where we are not allowed to make any demands on the base space of these RD bundles, holds in fact not just for many pairs, but for all. For all pairs I and D, where D is at least 6. So on the level of classifying spaces, what this means is that Pi for all I is non-trivial in the cohomology of B top 6. Okay. Right. But unfortunately, for example, for applications to diffeomorphism groups of disks that I might mention later, the second part of Michael's result is quite essential. And the main result that I want to talk about in these lectures is an improvement on the second part, which is based on Michael's original strategy. Just something that Alexander Kupers and I proved in a paper that will appear this year. Namely, we proved that the second part holds also all for holds also for all pairs I and D as soon as D is greater or equal to 6. And there are many equivalent ways of restating this result, some of which I would like to mention. The most immediate way of restating it that is analogous to this equivalent statement is that not only are these cohomology classes here trivial, they also evaluate non-trivially on the Hurewicz image. I can pick these homology classes to be coming from spheres. Okay, and I should also say that, in fact, this result of Søren and Oscar's is much more general than that, in that it shows that not only are the individual Pontryagin classes non-trivial, there are also no relations between these Pontryagin classes whatsoever, which is not something that we consider here. Okay, this is the first way of restating it. Another way of restating it is using a bit about the homotopy type of B top to see that this is in fact equivalent to the map from B top 6 to B top admitting a rational splitting after, let me write it out, after looping once. Okay, and yet another way of restating it that uses the smoothing theory that I was mentioning about is that certain characteristic classes of smooth disk bundles, and I don't want to say too much about this relation to diffeomorphism groups of disks. I'm very happy to discuss this in the exercise session if somebody's interested. But there are certain cohomology classes that are in degree, okay, I need to start I greater than d half for I minus d minus 1. And the claim is that these classes here are surjective. This map represented by these characteristic classes is surjective on rational homotopy groups. So in particular, B diff of a D disk for any D at least 6 has infinitely many non-trivial rational homotopy groups, and they have something to do with these topological Pontryagin classes. Okay. So for the rest of today and all my other lectures, I'm gonna give you as much of an idea of how to prove this result as possible. Pardon? Ah, sorry, yes. This was not a good right away. K, Q, and then this is degree. Absolutely, thank you. Yes. Okay. So what do we need to do? I mean, we need to come up with RD bundles with very low dimensional dimension, with low d, I mean d is equal to 6, and we need to produce them in a way that we can ensure that the ith Pontryagin class is non-trivial. And somehow this will be done in 2 steps. First, we're going to produce any RD bundle with non-trivial Pontryagin classes, and then, in a second step, we're going to argue that we can choose the base also to be a sphere. So sort of corresponding to these 2 parts in Michael's result. Okay, so how does one come up with RD bundles? I mean, we need to produce some to prove the result. One source of RD bundles I already mentioned to you, namely topological tangent bundles of topological manifold. We know some topological manifolds, we know some non-smoothable topological manifolds. We could hope that their tangent bundles, which are RD bundles, could help to proving this result. But unfortunately, this is no good. Why? If we evaluate the ith Pontryagin class on a tangent bundle of a topological manifold of, say, dimension d, then this lives in 4ith cohomology of M, but the cohomology of M vanishes above the dimension of the manifold. So in particular, in the range that we are interested in. So topological tangent bundles won't help us. What we do instead is, vaguely speaking, we use topological tangent bundles of families of topological manifold bundles. And I'm going to explain that in a moment. So let me tell you what I mean by the topological tangent bundle of a family of manifolds, unless there are any questions. Okay. Maybe to recap, what I told you so far is I reminded you of what Pontryagin classes are of vector bundles. I mentioned some historical developments that showed that in fact we can define them for more general objects called RD bundles, which are fiber bundles whose fibers are homeomorphic to RD. And then I was wondering whether these more general characteristic classes have the same properties as for vector bundles. I mentioned that Michael Weiss showed that the vanishing behavior is very different, and what I'm going to focus on for the rest of my lectures is an enhancement of Michael's result that shows that there are R6 bundles over spheres which have non-vanishing Pontryagin classes, and I can make the degree of the Pontryagin classes completely arbitrary. For any I, there is an R6 bundle over a 4I sphere that has vanishing ith Pontryagin class. Non-vanishing, thank you, very important. That's also correct, yes. Okay, so what do I mean by families of topological manifolds? Let me talk a little bit about M bundles. So let's say M is a closed topological D manifold. Then an M bundle is a fiber bundle whose fibers are homeomorphic to M. Okay, and any such M bundle has what's called a vertical topological tangent bundle. There is a vector bundle over the total space of this fiber bundle, not a vector bundle, an RD bundle, whose dimension is the dimension of the fiber. I'm going to call that T for tangent, little t for topological, and pi to make a reference to the bundle. And it has the property that on each, if I restrict it to each fiber, then this agrees with the topological tangent bundle of the manifold. Maybe you've seen this in the smooth setting. What one does here, roughly speaking, is one takes the tangent bundle of the total space and restricts to the subbundles of those vectors that are tangent to the fibers. If the bundle happens to be a smooth bundle, then there is a refinement of this to a vector bundle whose underlying RD bundle is this one. Okay. And now note that if we evaluate Pontryagin classes on these vertical tangent bundles of families of topological manifolds, then they live in degree 4i of the total space. So even if I is very big compared to the dimension of D, this could still be non-trivial because I can make the base to be very big dimensional. Okay, here in this generality, X is just a space. Yes, say a topological space. It need not be a manifold. Let me explain to you a general construction of how to obtain characteristic classes for such M bundles. If we start with a characteristic class, let's say in degree K, for RD bundles, then we get a characteristic class for M bundles by doing the following. We evaluate this characteristic class on the vertical tangent bundle of this M bundle. Then that is a cohomology class in the total space, and we integrate it along the fibers to obtain a cohomology class in the base space, which then is in the degree of the class I started with minus the dimension of the fiber over which I integrated. And universally, so this is called the kappa class associated to C, evaluated at that bundle. Universally, this gives a cohomology class in the classifying space for M bundles, which is the classifying space of the group of homeomorphisms of M. And if I find a topological M bundle such that kappa associated to a Pontryagin class is non-trivial, then in particular the Pontryagin class had to be non-trivial because this kappa class originated from taking the usual Pontryagin class of a vector bundle over the total space and then integrating. So we're going to search for M bundles such that the kappa class associated to the Pontryagin class is non-trivial. Okay. Unfortunately, that's not very much easier either, because typically the type of bundles that one writes down are smooth. For instance, by like writing down a submersion between smooth manifolds. And if the bundle is smooth, then this topological tangent bundle comes from the vector bundle. So the Pontryagin class that I evaluate here will be a Pontryagin class of a vector bundle. So it's going to vanish if the degree of the Pontryagin class is very large in compared to the dimension of the fibres. So then this fibre integral is also going to vanish. So we need to produce topological fibre bundle. We need to produce fibre bundles with fibre M that do not admit a smooth structure to have even a chance of this being true. And what we're going to do is we're not going to come up with such bundles out of nowhere. We're going to produce a recipe for starting with an M bundle and manipulating it in a way that does not necessarily preserve smoothness and that allows us to control the value of these kappa classes on those bundles. I'm going to make that precise in a moment. Okay. Any questions? Yes, I can. Yes. So let me do it in a special case so I can give an easy description. Let's say X is a manifold as well. Then this integration along the fibre is a Poincare dual to the induced map on homology. So I take this class, I take its Poincare dual class in homology, then I will get a degree shift. Then I use the induced map on homology to push it to a homology class in X. Then I use Poincare duality in X again, and then if you chase the degrees, you will land in this. But there is a construction that is more general, where X need not have Poincare duality, but maybe I'll tell you about it in the discussion session. Okay, all right. So as I was mentioning, the goal is to produce a method for manipulating M bundles that does not preserve smoothness, but that spits out M bundles where we have a control over the kappa classes. In order to state this method, one incarnation of it, I'm gonna need to remind you a little bit more about something about classical Pontryagin classes for vector bundles. Namely, I will tell you something about L classes and signatures. Okay. So there are very particular and important homogeneous polynomials in the Pontryagin classes called Hirzebruch's L classes. Li, they live in the 4ith cohomology of BO, so they also live in the 4th cohomology of B-top. Okay, they're homogeneous polynomials. The first two are the following. 1/3 of P1 is the first. The second is 7/45 P2 minus 1/45 P1 squared. A good topologist knows these numbers by heart, but I don't. Okay, and so on and so forth. in general, the property that's going to be important for us is that the leading coefficient in this homogeneous polynomial, which is the rational number in front of pi, where I is the same as the degree here, is always non-trivial. So it's some coefficient times pi plus something like linear combinations of multiples of decomposable Pontryagin classes. Decomposables. Okay. What makes them special is the Hirzebruch signature theorem. Let me just mention it in words. If you start with a 4I manifold and everything is oriented, you evaluate these L classes on its tangent bundle, and you evaluate it against the fundamental class, then you get a number, and that number agrees with the signature of the manifold. What I need is a slight generalization to this, to M bundles, which is called the family signature theorem. So E to X is an M bundle. And the statement is that there is an equality of characteristic classes. Sigma I of pi is kappa associated to this L class of pi, which is in degree 4i minus d of x. The right-hand side I've already defined. It's this kappa class. What is the left-hand side? So sigma I is, let me describe it as follows. It's the unique characteristic class of M bundles. This chalk is very annoying. Okay, of M bundles. Such that if I evaluate it against an M bundle, where X is a 4i minus d dimensional manifold that is stably parallelizable, then kappa associated to the L class lands in 4i minus d cohomology of X, which is the top cohomology. So this class is just given by a number, and that number agrees with the signature of the total space, which is a 4i dimensional manifold. So the signature of the intersection form on E. Okay, maybe as an exercise, you can show that there is indeed a unique characteristic class of M bundles with this property. Okay. What I'm going to use from this is that if one looks at this, one realizes that in fact this depends on less structure than an M bundle. To make sense of the signature of the total space, I only need to know that the total space is a space that satisfies Poincare duality. So what this shows is that these kappa Li's, they only depend on the underlying vibration of the M bundle. I am not using the sort of structure as a topological fiber bundle to compute the values of these kappa classes, which is very special for these kappa classes associated to the L class, similar to the fact that the signature of a manifold only depends on the underlying Poincare complex. So the L class of the tangent bundle of the manifold also only makes sense from Poincare complexes. Okay. All right. Let's continue. Oh, this is one reason why I was looking forward to coming to Copenhagen. Very nice. Okay, how am I doing in time? Oh, all right. Okay, so let me state the result and then reduce the main result to this. And for the purpose of these lectures, we're not going to call it like that in the paper, but let me refer to it as the bundle manipulation theorem. So the situation is the following. We're having a closed d-dimensional topological manifold. The dimension is at least 6, and M is 2 connected and stably parallelizable. Okay. Then I have an M bundle. That comes with a trivial disk subbundle. Okay, so what does that mean? I have an M bundle here, pi, and maybe before I state this, let me fix an embedded disk of codimension 0 once and for all in M. And there's an M bundle here, and I'm saying there's an embedding of a trivial disk bundle into E, let's call it E, such that on each fibres, this is the inclusion of the disk in M. Okay, so a little more structure than just an M bundle. And if we have that, let me write E lower circle for the space that I obtained by cutting out the image of this embedding from the total space. Or rather, the image of the interior of the disk times x from the total space. Then the pi restricts to a map to x. And this is a new fiber bundle whose fiber is now M without a disk. Which I denote as M lower upper circle. Okay, and this bundle, let me write it as pi lower circle. So how does that look like? Let's say our bundle looks like this. The fiber is a circle. Then I have a trivial embedded disk bundle in here. And if I cut it out, then I get a bundle that looks like this. Oh dear, should have practiced this. Okay, so this is pi, and this is pi up circle. Okay. So here's the technical result that we're going to show in order to prove the main result. So it's this, what I'm going to refer to as the bundle manipulation theorem. Now, it says that if an additional condition is satisfied in this situation, namely, if the vertical tangent bundle of this fiber bundle where I cut out the trivial disk bundle, if that splits off a trivial plane bundle, then I can produce a new M bundle. The statement is there exists an M bundle. Let's call it pi tilde, E tilde to X tilde. It's over the same base space. It also comes with a trivial disk bundle. E tilde. And it has the following properties. We'll call it A. First of all, I have not changed the values of the kappa classes associated to the L classes. Second, all the kappa classes associated to decomposable Pontryagin classes vanish. So for example, something like p 2000 to the cubed vanishes. Okay, then there are two more technical conditions that I'm going to use, or not conditions, conclusions that I'm going to use in the proof. The first one is not so technical. It just says that pi tilde and pi as vibrations, they agree. They have the same underlying vibration, meaning there's a fiber homotopy equivalence between them. This is A prime, and then there's B prime, which says that if I take the vertical tangent bundle of this fiber bundle that I obtain by cutting out the trivial disk bundle in my new bundle, so this is now classified by a map from the new total space without this disk bundle to B top D, then that vector bundle is rationally trivial in the sense that this map is rationally null homotopic. Okay. All right. So the reason I call them A prime and B prime is that A prime in fact implies A and B prime implies B. So these are stronger conclusions. So A prime implies A. Why is that? If I have two bundles who have the same underlying vibrations, then I'm claiming I know that their kappa classes associated to the L class agree. Okay, well, I told you about this earlier. This is the family signature theorem. A little more technical, and I might explain that in the discussion session if somebody is interested, is the implication between B prime and from B prime to B. And in fact, for that implication, I need to strengthen B prime a little bit, which I'm going to do now. So let me fix a base point in the boundary of M tilde. Remember, this M's lower, no, not M tilde, M upper circle is obtained by cutting out the interior of a disk in M, so the boundary is a sphere. Let's fix some base point. Then what this gives in particular is a section of this bundle if I send little x to this base point times x. And I want that, well, first of all, the vertical tangent bundle restricted to this trivial disk bundle comes with a trivialization that comes from the trivialization of that bundle. And I want that this rational trivialization agrees if I restrict to the image of that section with the given realization. Sorry, not trivial. Trivialization. So this is a minor point that you can safely ignore, but in order to prove this implication, this is actually essential. Okay. All right. So, yes, of course. We're going to get to all of that. Say again, this you mean about Pontryagin classes? No. So, okay, maybe I should have said this. Our proof is completely independent of, I mean, yeah, these two results, of, like the result of CERN and Oscar and ours, they're independent in terms of methods and also in terms of results, because what they show does not imply what we show, and what we show does also not imply the stronger version of what they show in the sense that there are no relations between them. Yes, we're not going to use that. Okay, but we're going to use a different result of theirs. I'm going to explain you in a bit. Let's suppose for a moment that we are good at producing certain M bundles. namely bundles where kappa of Li is non-trivial. So let's suppose for a moment we knew the following. Let's suppose that we know that for all I, there is an M bundle. Let's say I and D greater or equal to 6. There's an M bundle, pi from E to B, such that the kappa class associated to this bundle is non-trivial. Okay, I'm going to assume that for a moment, and I'll tell you a little bit later about this condition. So let's prove the main result, assuming this existence of these bundles, the existence of these bundles, and this bundle manipulation theorem. Oh, I want to keep that. Okay, how does that go? All right, here comes the proof. Let's write the L class as we did previously already, a multiple of the Pontryagin class of the same degree, and a sum of multiples of decomposable Pontryagin classes in the monomials in the Pontryagin classes. Okay, so let's take some I and some dimension d greater or equal to 6, and using this property star, we're going to pick an M bundle pi from E to X such that the kappa class associated to the L class is non-trivial. Okay, then we can do the following. Well, we know this is non-trivial by A prime, no, by A in the bundle manipulation theorem. We know that the value of that agrees with the new bundle that we get as a result of applying this manipulation theorem. Now we can write this out. Yes, I do have an assumption. Okay, yes, as in bundle manipulation theorem. I can pick M to be two connected, stably polarizable, and I can pick this bundle to have a trivial D subbundle. Yes, thanks. Okay, now these kappa classes, they are linear with respect to the characteristic class of RD bundles that I plug in. So I can write this as the kappa class A times the kappa class of Pi plus the kappa class associated to some decomposable characteristic class. Now by B, this vanishes. So we know that this guy here is non-trivial. So kappa of Pi of pi tilde has to be non-trivial. So Pi is non-trivial in as a characteristic class of d-dimensional of RD bundles. But the result promised more. The result promised that I can choose the base of the RD bundle for which Pi is non-trivial to be a sphere. So let's argue why that is. Do I want to keep this? No. No. Yeah. Okay, so what's left is that Pi, which I've already shown, is non-trivial, evaluates non-trivially against the Hurewicz image. So I find a homology class represented by a sphere on which it is non-trivial. And this is where this condition B prime, the stronger conclusion B prime, will be essential. Here it is. So let's do the following. let's take our bundle. That is the result that we used which we used to show that pi is non-trivial. Now, the Pontryagin class is represented by, well, let's take the vertical tangent bundle of this bundle. This goes to B top D. Okay, let's represent the Pontryagin class by a map to an Eilenberg-MacLane space, and let's look at the subbundle that I obtain by cutting out this trivial disk bundle. Then I know, because of this condition, that rationally the restriction of the vertical tangent bundle of pi tilde to E tilde circle is trivial. So let's say we work rationally here, then I find a null homotopy here. Okay. Now, because I've argued already that kappa pi for pi tilde is non-trivial, this composition here is not null homotopic. So if I view this square as a relative cohomology class in degree 4i of E tilde relative to this subspace, then this is also non-trivial. But then I observe that this fits into a push-out. Right. Here's the boundary bundle of this, and here's the disk bundle. This is a push-out by definition of this subspace. Okay, so that means that the relative class that is given by the whole decomposition is non-trivial, so the map on cofibers is non-trivial. But if I take the cofiber of that, then this is the default suspension of X with a disjoint base point. So in particular, I mean, if D is at least 6, this is a simply connected suspension, so its rational Hurewicz homomorphism will be surjective, and any cohomology class that is non-trivial in here, I can represent by something over a sphere. That's how you get the stronger statement about bundles over spheres. And note that this is very inexplicit. I've not given to you a map from a sphere in here that such that this composition is not null homotopic, but I've explained to you that there is a promise that there exists some. Okay. So I guess I started 2 minutes late, so I have 2 more minutes. And that is exactly enough to explain to you something about the star condition that I think I removed, and yes, and what happens in the next lectures. Okay, so remember the star condition. In some sense, what I did so far seemed a bit tautological, because I assumed the existence of certain bundles with non-vanishing kappa classes associated to the L class that have something to do with Pontryagin classes. So why didn't I basically assume the conclusion of the result and then did some complicated maneuvering to say, okay, then I can also represent it over a sphere, but essentially I already knew that it's non-trivial. The reason is the following. In the star condition, I only assumed that kappa Li of this bundle is non-trivial. But kappa Li can be non-trivial for many different reasons. It need not be that kappa of pi of this bundle is non-trivial, because very low-dimensional Pontryagin classes and then high powers of them can contribute to the non-triviality of this bundle. So even when the bundle is smooth and the fiber dimension is very small with respect to I, kappa Li can be non-trivial, because there can be very low-dimensional Pontryagin classes and powers of those that contribute to the non-triviality of that. So to find bundles of where I is very large and the fiber dimension is very low, such that kappa Li of pi is non-trivial, we can try to use smooth bundles. And we're much better at producing smooth bundles. And in fact, sort of the existence of smooth bundles with certain properties of characteristic classes is like, we understand like very well since some years due to work of Søren Galatius and Oscar Randall Williams. So what they do, in particular, implies the star condition very directly, including all these additional assumptions that I wanted. So the upshot is that we already know that there are very nice smooth bundles. The fibres is very simple. We can pick M to be like essentially as nice as we want. they tell us that there are bundles with non-trivial kappa classes associated to the Li. Then there is this sort of big black box that tells you, this bundle manipulation theorem that tells you whenever you have given a bundle, even a smooth bundle, forget that it's smooth, consider it as an M bundle, then there is a very weird process that spits out a new bundle, and I'm going to prove the existence of this weird process in the next two lectures, and that changes the behavior on kappa classes drastically. It puts all the kappa classes associated to decomposable Pontryagin classes to 0, and it still keeps the non-triviality of the L classes, so the contribution why kappa of Li is non-trivial suddenly must be in the leading coefficient. And this is how one shows that kappa of Pi is non-trivial. In the next two lectures, I'm going to give you the proof of this bundle manipulation theorem. Thank you. Yes. Let me walk you through this diagram again. I've already argued before I started drawing this diagram that this composition here is non-trivial. That's Pi of the total space of this new bundle. Okay. And I've used then this condition here that the tangent bundle of this, the vertical tangent bundle, which is classified by that map, is rationally null homotopic if I restrict it to this bundle where I cut out this trivial disk bundle. So if I rationalize this space, then that means this composition here is null homotopic. I can choose a null homotopy, which gives me a homotopy which gives me a witness for this square being homotopic. Okay, because this map here is non-trivial, this outer square considered as a relative cohomology class, so as a class in degree 4i of E tilde relative to E tilde with a circle, is also non-trivial, because the absolute cohomology class is already non-trivial. Then I've observed that this E tilde is obtained by a push-out by gluing back in the trivial bundle that I cut out to the one where I cut it out. Okay, so because push-outs induce isomorphisms on a relative cohomology, I know that the big outer square is non-trivial as a relative cohomology class. Now it's no longer true that just the bottom map, the absolute cohomology class, is non-trivial, but it's non-trivial as a relative cohomology class. In other words, by excision, the relative cohomology is the cohomology of the quotient, so the cofibre of this map. I can view this as an absolute cohomology class of the cofibre of this, which is a default suspension of X plus. So I know that this map here is non-trivial. And now the point was that for suspensions, I know that rationally all non-trivial cohomology classes are I find a map from a sphere that evaluates non-trivially against them. This is some general result about the rational homotopy type of simply connected suspensions. So the input here that I'm using is that the rational Hurewicz theorem for, let's say, for any suspension that is simply connected is surjective. Maybe I need to assume some finite type assumptions, but these assumptions are given in this case. Okay. Any other question? Sorry? No. It's in both. It's in the proof of the BMT and in this one. Yes. Pardon? Yeah, okay. I think to have the star, I can probably push D to be even smaller, but the proof of this bundle manipulation theorem will certainly use dimension 6. Maybe it can be pushed to dimension 5, but yeah. Yes. I don't think that's known. Yes.